T infinity 1 minus T infinity 2 over resistance total. That's what we're solving for. So technically, the most challenging part now is to solve for R1, RI, R1, R2, R resistance in para, R6, and RO, which we have to be looking at the individual concept. And that's where the solution is going to end quickly. Now let me give you a hint on that. Read the question carefully. At ROI, let us look at ROI. ROI, so now we are solving for individual resistance. And we can see that we have ROI, which is 1 over H1 AY, because this section was undergoing convection heat transfer process. This section was undergoing convection heat transfer process. And then what is the area for that section? Then it comes now, what is the area for that section? Now I'm going to explain the logic. See that there is a section which we have a measurement, which is this measurement. We have 1.5 plus 22 plus 1.5, that gives us what? That gives us 25. That gives us 25 centimeter, which is equal to what? Which is equal to 0.25 meter. What you should know is that brick is being the same brick that appears to be above and below. So there is a repetition of the same dimension in this problem. So the construction of the wall repeats in every 25 centimeter distance. So take note. The construction of the wall repeat after every 25 centimeter, which is equal to what? 0.25 meter. There is a repetition. But along the horizontal direction, no variation is given. So that 25 centimeter that you see, which is 0.25 meter, is a repetition that occurs in the vertical direction. So this is a repetition. Repeat in the vertical direction. Repeat in the vertical direction. So you repeat in this vertical direction. You repeat in this vertical direction. But no variation is given in horizontal direction. We are not given any variation in horizontal direction. So no variation is given in the horizontal direction. And the question is, should we take 0 we can't take 0 because a dimension exists but it has not been given. And in a case whereby a dimension is not given, we have to consider a standard depth of 1 meter. In a case like this, we consider a standard depth of what? 1 meter. Depth must be considered because the area of the material exists, and therefore this area now will become what? 0.25 times 1 meter square. That's the area for that break, which is repeating after every 25 centimeter. So have that clear in your mind. And therefore, you're gonna see that in this problem, this H value, the value for H1 was given as 10 W per meter square times Kelvin. Was given as what? Was given as 10 W per meter square times what? Times Kelvin. So we can calculate that ROI for convection process. So this has been calculated. Now we move to what? We move to RO1. RO1. What is RO1? RO1 is this material which I spoke about. And RO1 is actually the foam material. It is actually the foam material. So RO1 is equal to FOAM is the foam, which is equal to what? The foam give us a scenario of what? Conduction. So L over Ka. So I'm talking about RO1, which is foam. RO1, which is foam, equal to what? L over Ka. What is that length? Look carefully. It is given in the problem. Look at this dimension here. This is the length. That is the length for each of the material. That is the length for foam. This is the length for plaster. That is the length for brick. That is the length for plaster. So we have that length given, and we need to convert that to meter. So that becomes what? 0.3 meter, and the K for that value is equal to what? 0.026, and the area for that is equal to what? 0.25 times 1 meter square, because I've already explained that area. Now we move to what? We move to RO2, which is equal to what? RO6, which is equal to what? RO plaster, which is equal to what? L over Ka. So RO2. So this is RO2. This is RO2. Sorry, this is RO2. This is RO2, which is equal to RO6. So this is plaster and plaster. It is RO6. It is the same material, so I'm just simplifying. In that context, what is the length? Look at the length for that material. It is actually 2. So this is it. It is 2 here. It is 2 here. I have to convert that to meter. I have 0.02 meter, and the value for K for that is 0.22 W per meter times Kelvin, and the area becomes what? Area is 0.25 times 1 meter square, and therefore we can move forward. We can move toward arrow 3 equal to arrow 5 equal to arrow plaster at the center. And that section is exposed to what? It's exposed to conduction, L over what? Ka. What is the value for the length? Look at the center. The center, the length is 16. It is 16. I have 16, which if I convert that to meter, I'm going to have 0.16. And this value is 0.22. And this is 0.015 times 1 meter square. How do we get that? How do we get that? That is just the brick section we're talking about. And we're talking about a particular section for that, which was actually having an area of 0.5, because that plaster is having just the thickness of its plaster. So the area of that plaster becomes just this area, which we have 1.5 centimeter times what? A given depth, which is 1 meter square. So this is area of plaster times, which is what? 0.015 times the depth, which is what? 1 meter square. And that's just what we are doing using for multiplication. And then I've told you how to solve for the resistance that are in series. If you do that, you can now solve for what? You can now solve for rate of heat transfer for the problem, because you obviously know that the arrow midway, which is actually going to be solved later when I solve for arrow 4, which is going to be the resistance for the brick, and that brick is having this value for the resistance, which is and the length for that is going to be what? Is for that section for the brick, we are going to have a length of 16, which is this. Arrow 4 gave us a brick which has a length of 16. So that is the length of the brick, which is 16. And if you convert that 16 to meter, we're gonna have about 0.16 meter, and then it has its own area now. If you look at the area for that brick, the brick has an area of what? 22. So the brick has an area of 22. That is the brick area, 22, and that's the length, 16. So it has an area of 22 with a given depth of 1 meter square. So that will become what? 0.22 times 1 meter square. And this value for K is 0.72 W meter square times Kelvin. And now we are talking about arrow O, which is arrow convection, which is equal to 1 over H2 A2. And that conversion process is given as what? Is given as what? 25 W meter square times Kelvin, and the area for that is equal to what? 0.25 times 1 meter square. That is equal to 0.25 times 0.25 0.25 times 1 meter square. So that is the resistance for that outer section, and we know for sure that the resistance which are in series are different from that which are in para. So for the resistance which is in para, arrow midway, for that which is in para, we are going to have a value of what? 1 over 48.48. If you sum that value for that arrow 5, that is actually, this is actually arrow 3, and we're gonna have 1 over what? 1.01. This is going to be equal to what? Arrow 4 plus 1 over 48.48, which was equal to what? Arrow 5. So if you simplify that further, you're gonna have a value of what? A value of 1.03 per degree Celsius. And if we solve for this arrow, we're gonna have what? We're gonna have, which we are dividing that by 1 divided by that value, we're gonna have 0.97, because this value is effectively, we divide that, so it's identical to what? 1 divided by that value, 1.03. That's what actually happened to get that value, and therefore we know that the total the arrow resistance total for the system will become what? Will become arrow 1 plus arrow 2 plus arrow mid plus arrow 6 plus arrow O, gonna give us what? Gonna give us 6.87 degrees Celsius. So the rate of heat transfer for the system will become what? T infinity 1 minus T infinity 2 over arrow total. That will give us 20 minus 10, all that in degrees Celsius, over 6.87. Remember, T infinity 1, if you look at the data, we have T infinity 1 and T infinity 2. Those are the value which we substituted here. And that is how we solve for that problem. And in that context, we have the answer as 4.37 watt. So that is the solution for the first exercise for today. I hope this video is going to help you to be able to do some class exercise on Monday in class. Let me do the last video before I go to where I'm supposed to go to. It's Saturday, but I felt like I should do this to make sure you understand what was going on in class on Friday much better. Thank you all. God bless you.